The concept of hybridization can be mysterious and a bit confusing, so just expect that. But I will do my very best to clearly and concisely give you an idea of why do we think there's this concept of atomic orbitals hybridizing, how that is directly linked to our VSEPR geometries, and ultimately, what do you have to do as an AP student with hybridization as far as questions and expected knowledge? I'm going to go ahead and switch to the document camera, and then we will dig in. All right. One approach to bonding is that you'll create a covalent bond when two atomic orbitals overlap and each of the elements, so we'd have an overlap of their electron clouds, and that each donates one electron, each atom. So one would be coming from A and one be coming from B. And a lot of our Lewis dot structures showed us that. But then there's a little confusion and mystery about, well, if that is true, how exactly are we getting tetrahedral, trigonal, bipyramidal? So the best example to walk us through that is methane. Methane has carbon, and we measure that the single bonds are distributed with bond angles of 109.5 degrees, and that we get what we name tetrahedral, the tripod. We know this. Well, here's our electron configuration. So the orbitals that carbon presents for bonding would be an S in the second energy level, and then 3p on, let's call that the X, the Y, and then the Z. Well, a little bit of the first mystery, we're saying that atomic orbitals have to overlap. And so if hydrogen is coming in with its single electron in the 1s, well, there's only two singly traveling electrons in carbon to bond. So we actually think that, all right, as part of the process, one of these two s electrons must get promoted. It must, because if it's forming four bonds and bonding happens in the overlap of the orbitals, well, then that must occur as part of the process, then making four electrons from carbon available to make four single bonds with hydrogen. But then we'd still have the overlap of S, and then we'd have to overlap in the P, the Y, and then a Z P orbital. Well, these are separated by 90 degrees. So if the overlap is happening with these orbitals, then why aren't the bond angles 90 degrees if the hydrogen is coming in, and we have to overlap, and then the hydrogen is coming in? Why aren't we getting the 90? Why 109.5? So our prediction is this. Our prediction is that carbon actually hybridizes its orbitals. So we have the promotion, and in essence, what we think occurs is that the s orbital is then hybridized or mixed. Sorry, that's a very bad px. And s and three of the p orbitals get mixed. So imagine putting into a blender, and then what we get out of the blender would be the same number of orbitals we put in, but now each is a mixture of S and 3p. So the resultant is going to resemble a little bit more of a p orbital because we're adding 3 p's and 1 s. And so if you could imagine, we'll get something instead of S and P, has a little S, but then a lot of P. That's the predicted mathematical shape. But these, so we would get 1, 2, 3, 4 of these. And when you put these together, sorry, they're supposed to be identical. Well, then you'll find them on a 109.5 bond angle. And they measure the same energy, all 4 of them. So it's no longer the S is of a lower energy. That would result in most likely a shorter bond than these, but they're all identical. So probably these 4, a little bit less than the 2p, but a little higher in energy than the 2s, because only one of these was combined. So since we made 4 new out of 1s, but 1, 2, 3 p's, we call it sp3 hybridized. Only 1s and 3 p's. So to get this geometry, if we would start with the Lewis dot structure of methane, and we understand, okay, carbon is creating 1, 2, 3, 4 electron areas. Well, we're always going to be bonding with valence, and we know valence are going to be found in the S and the P. And we know the S sublevel only has 1 S orbital, the P has 3. So to create 4 areas of equal length, equal energy, we say 1, 2, 3, 4, S1, P3, that the carbon here is sp3 hybridized. So you'll have the geometry or something telling you the shape or the number of bonded areas, or you have the Lewis dot structure, or you have the molecular geometry shape. We need to just be able to determine the number of electron areas or the number of sigma bonds. Sigma bonds occur in hybridized orbitals. So this is the way that we would go. And then we would say that carbon is sp3 hybridized there. What if we were given carbon dioxide and asked, what is the hybridization on the carbon in carbon dioxide? Well, there are 2 areas of bonding, 2 electron regions. We know we are going to be bonding with S and P, the valence. Well, there's only 2. So these are being blended to create, and so that would be if, the S is here and the P is here as far as energy, well then mixing 1s and 1p would give us in between those energies. And we made these mixed orbitals out of 1s and 1p. So these are sp hybridized orbitals. And then 2 of them with carbon would remain unhybridized. So we would say here that carbon is sp hybridized. That's where the sigma bonding, if the pair that we wrote on the bottom, who knows, is occurring in the plane of the nuclei, the sigma and sigma. We only have 2 hybridized. That gives the linear geometry of 180 degrees separation. These unhybridized orbitals are where the pi bonds form. So carbon here is sp hybridized. Well, what if we were asked, what is the hybridization on one of these end carbons? Well, on the end carbon, on the end oxygen. So there would be 1, 2, 3 areas of electrons. We count lone pairs as well. Well, oxygen will bond with its S and its P, but here we need 3. So 1, 2, 3. The Hybridized orbitals would then be putting in 3 atomic, and we get 3 hybridized then out, 1 of the S and 2 of the P. 1 remains unhybridized. And so we would say that oxygen is bonding with sp2. Of course, these aren't bonded. Those are where those electron pairs would reside. One of these is the sigma bond, and the unhybridized is where the double bond would be. But we just have to know how to predict the letter designation of hybridization. So I found some visuals. So if one s orbital is blended with a p, 1 and 1, so we're going to get 2 hybridized, and they're a blend. You'll never have to draw these. I just hope it's giving us just a good visualization of the result. And when they overlap, that's nuclei and nuclei, when not the black dot, they're, I guess, quote unquote, showing you, oh, well, no, I think that's where the electron will then reside, but over this whole area we know. And so when we overlap them, this is one area and one area. And then these overlap for bonding. And so if here's our nucleus of carbon, well, then here is the overlap, there's the overlap. That's how we're getting 180-degree bond separation, of course. Okay, if 3 orbitals, well, then what will result is a blend of these 3 in, 3 out. When they distribute, we get our trigonal planar instead of 90 degrees. And then here's our 4, how we get the tetrahedral. Okay, so again, what are we gonna have to do with this? Well, I borrowed this text from the most recent edition of Chemistry written by Chang. If you want to take a moment and read this. Hybridization is our creation, our creation. It's our attempt to try to explain why things are as they are. This is a little confusing, and we know that, but this does connect for us why we get our different geometries. Okay, so what do we have to do with this? Well, usually we ourselves are creating the Lewis dot structure. We then would count the number of electron areas and then connect that to what we would call the hybridized orbitals. So here's just another kind of organized chart with some examples. And I'd love to show you a specific problem. All right, so draw the Lewis structure for HCN. Well, that would look like this. Which hybrid orbitals are used? Well, let's start with carbon. Carbon has 2 areas of electrons. So this would be sp hybridized. Nitrogen has 2 areas. This would be sp hybridized. Hydrogen just has 1. It doesn't need to blend. It just has the S. So this doesn't have a hybridized orbital. Then, of course, show all bonds, label as sigma or pi. So we know one of these, or this is a sigma. And we know one of these, and it doesn't matter, just one of them. So maybe I'll choose this bottom one to be the sigma, and then this would be pi and pi. That's a little, I don't want that to be misinterpreted. So the triple bond would be 1 sigma and then 2 pi bonds. And this is simply 1 sigma bond. So we needed 2 hybridized. Nitrogen needed 2 hybridized for its lone pair and then the sigma. So we have 2 sigmas on carbon. That's what we needed to hybridize. And then the 2 additional are going to be the unhybridized orbitals. And we know that p orbitals will be above and below. And if we want to say this is the x-axis, then in front and in back. On nitrogen, above and below, in front and in back. So it's the bringing together of the y-axis orbitals that will accommodate one of the pairs, and then another in the front and in the back. Isn't that how we defined pi bonding? It's outside the plane of the nuclei. Here, the carbon, sp hybridized. So it has one of those hybridized orbitals, another hybridized orbital with a little thing. Nitrogen, one hybridized orbital, and then, oh, sugar. We would put the lone pair. I just did that from the Lewis dot over here. Toot, toot. Okay, so the hybridized orbitals are, we wouldn't call this a bond, but there's the sigma and then the sigma. And so here is where we have our multiple bonding. So if we take a look, here is C2H4. Carbon is double bonded. So the carbon here, 1, 2, 3 areas of electrons, so S and 3p. So we are blending 1, 2, 3 orbitals to accommodate equal energy, equal length. So it's sp2 hybridized. There's going to be 3 hybridized orbitals. So on this carbon, here's one, here's another, and here's another. Now, this would be our hydrogen, non-hybridized. On this carbon, same thing. 1, 2, 3. We have an unhybridized, and that's where they're showing outside the plane of the nuclei. And they're choosing to show it above and below. But of course, it could be in front and in back, the z-axis. Here is a representation of a triple bonded carbon. So it's only sp hybridized. There's the 2 hybridized on that carbon, the 2 on that carbon, and then a pi bond above and below, and a pi bond in front and in back. So the geometries that we went through are actually, connected or related to electron areas. And so linear, sp hybridized, 1, 2 electron areas. Trigonal planar, sp2. Tetrahedral, sp3. And of course, it's that same hybridization if they're lone pairs. Now, we have experimental evidence that backs up this theory of hybridization. Absolutely. Now, when we first developed the idea of hybridization, we also had sp3d. Sorry, that's in that order. That's kind of weird. So we know that there are elements that exceed the octet. How do they do that? Well, bonding happens in the S and the P. And again, I'm drawing them at different heights as if energy. And then D. Now, if an element has D available, D orbitals, well, it can blend those. So what if we would need 5 areas of bonding, like we do in trigonal bipyramidal? 5 areas. Well, we'd have to blend 1s, 3p, and 1d. That would be sp3d hybridized. And then 6 would be s, 3p's, and 2d's. sp3d2. These are in question. The experimental data does not back these up, these hybridizations, as much as these. So the College Board will only ask you about these, but your textbooks will also refer to those. I hope that this provided some clarification, showed us exactly the types of questions that we'll have to answer, from the Lewis dot structure, create, or just refer to the hybridization correctly that we'll see on whichever carbon is identified or element is identified. So you'll see in the unit assignment and any practice problems, this is what we're asked to do. Of course, you can see me with any questions or concerns. Thank you.